Okay, everybody. Welcome back after a month or so from when I sort of piloted this thing. Got to do some housekeeping and then a short presentation. So let me post. I don't really have a super slick operation here yet. So let me get all set up. Messing around with the YouTube studio. I can't find anything all the time. And so we need to look at that again. I need to find where everything is around here. Gonna throw a link into the Discord for people. Then I'm gonna post one on Threads, which is if you're not aware, Meta recently launched sort of a competitor to Twitter. I'm no longer on Twitter. I'm on Threads now. Seems to be going pretty good. After the stream, I'll post something in the Discord about that, where my profile is. But everybody hear me out there? Because someone could type into the YouTube chat or on the Discord, let me know if you can hear me. That would help a lot. So I look at two things. There's the there's the chat on the right side of the YouTube video, and then we have the Discord. That you're welcome to join. The link for the Discord server should be in the channel bio. So if you want to check that out, I'll be watching both. And so we're gonna do a short presentation because I've sort of come to some conclusions on how I want to move forward with this over the next couple months. And, of course, always welcome for your feedback on that. And any other questions that you have during the stream. I'm probably going to be a shorter one today just to get sort of warmed back up. Working on the linear slide assembly that I was doing a month and a half ago, I think. So we got to finish that up in the next week or so. And then we can talk about where we're going to go next. But yeah, so YouTube chat and Discord, I'll be watching those. And any questions or comments are welcome. And let's look at a presentation of sorts. There's only 4 slides, but it actually took me quite some time to land on what I wanted to do with this channel and with this effort, I guess. All right, great. So, basic overview of how the YouTube channel will work. This is my current thinking. Again, subject to change. But there'll be work sessions, which I've already been doing. So that'll be 2 to 4 hour, very informal, open door sessions where I'll be using mostly OnShape CAD. And the reason for that is that OnShape is free. You don't have to pay for it. The catch is that your designs are essentially open source, freely available to anyone else on OnShape. I don't really care about that personally, but you might if you don't want your designs publicly shared, you have to pay for it. But I'm doing it so that you can, if you're interested in maybe you've never used a CAD system before, maybe you're new to all this, but you'd like to learn, you can grab my designs in OnShape and you can essentially copy them over to your little workspace in OnShape. And you can explore or modify the designs, and I'd like to see that, because that means that you're really interested in doing that, interested in the work. But that's why I selected OnShape. The other program we will be using shortly is Fusion 360, which is made by a company called Autodesk, and right now OnShape lacks computer-aided manufacturing features. So as I explained in the last live stream months ago, one thing that I want to do is I don't want to just show how real machinery is designed, but also how it's manufactured, because those two are commingled continuously. Those two aspects. There's no sense designing something if you can't manufacture it, and so you have to know how to manufacture it. And so we will be using digital tools in conjunction with mechanical CAD to show how things are actually manufactured. It's very important. Okay. The second type of event, I guess, is going to be what I call breakout sessions. The work sessions are going to be mostly me silently working, hopefully in time. Others will join in with questions and comments, and so I'll be talking a lot during the work sessions as I'm working in OnShape. But the breakout sessions are going to be more like a classroom environment, sort of, where I'm talking about teaching about something that I designed in a previous work session. So there's no sense in me designing something in CAD if you're not familiar with it, and no one's explaining why I'm doing what I'm doing and how to actually make engineering decisions on how to design your own machinery. All right, so that'll be a breakout session, and I'll keep it relatively short and to the point. A lot of this stuff is very technical. A lot of it's going to be very new if you've never thought about designing machinery or robots before. and it's going to take a while. So we want to do it. We want to do it slow, but we want to be impactful with it. We want so about 30 to 60 minute, short presentation to kind of show you exactly what's going on, and we'll do a bunch of those as needed to fully explain what is happening. And then workshops is going to be sort of the grander event. A 4-day series in a row, I'm thinking, of a larger topic. And I have the first workshop in my mind right now, which I will talk about in a minute. But the hope is that it'll be live streamed on YouTube. But the hope is for some of it to do a physical workshop, which is going to require some venue coordination. I'm in Detroit, if you don't know that already, and there's lots of potential opportunities to do a physical workshop. It's a little tricky. A lot of this work is a little tricky to do because we're talking about machinery, we're talking about working with components that are costly, especially industrial grade control systems and stuff like that. But in time, I think there's some ways to make it work. So we'll have to start light with that. But in time, we'll find a groove to go into to do that. Okay, so the live stream schedule that I'm hoping to keep to from here on out is I'll be doing work sessions Monday, Wednesdays, Fridays around 7 p.m. Eastern Standard Time. And then we'll do a breakout session every Sunday at the same time. We'll start with this time of day right now, see how it goes, do a couple months of it, and then we'll, if we get kind of a bigger audience, we'll kind of see where people want to push and pull things in terms of schedule. I think it's late enough, maybe not on the West Coast, but I think it's in the ballpark for late enough where people can participate. But we got some work to do on that. But for right now, this is what I'll try to keep to. So we won't be doing a breakout session this coming Sunday because I'm not prepared for it, but we will start doing those the next Sunday after that. Okay, so design path. Here is what I'm currently thinking in terms of the machinery that we will explore. Take some time to go through all this, many months, probably many years, definitely many years. We're on the linear slide assembly now, which is sort of really one of the more basic pieces of industrial equipment that exists. Not the most basic, but a pretty good start. Then we'll go to a gantry robot. Don't worry if you don't know exactly what this means. The linear slide assembly that we're on now is a little odd because I'm just trying this format out. I'm just getting this program started. But in the future, what I think we need to do, what I need to do is that and maybe more in time, if others want to participate, is we need to do sort of an initial design review to kind of get the full-ish engineering experience. How you kind of plan out an initial design and then design it, and then do sort of a design review on what you did. With the linear slide assembly I'm doing now, I sort of jumped into it. I just sort of jumped in. But in the subsequent ones, I think we need a little bit more upfront explanation about the decision process and where things need to go. So part of that will be kind of sketching out in some way how these pieces of industrial equipment will look. And then we can go into the actual nuts and bolts, the design of it. So we'll do a gantry robot, we'll do a small automation cell, we'll do a large tank welder, we'll do a seam resistance welder, and we'll do a dual turret wire bender. All this equipment I have done in my career, designed in my career. Pretty competent in how to do it start to finish. Some stuff is a little fuzzy. I won't. If there's something I'm not competent on, I won't just wing it. I'll explain where. No one knows everything. I mean, it's a very complex industry. And so there's some areas that I'm not familiar with, and if I'm not familiar with them, I'll talk about them. And maybe in time, if there's some audience members that are engineers that are competent in these areas, they can join me, and we can fill in the blanks. But that's sort of a longer term, I think, issue. Okay. And the last slide is the first workshop that I'm planning is entitled Industrial Program with Python and Julia. Okay, Python's a programming language, and Julia is a relatively newer language that I think has a lot of promise, particularly in system modeling and simulation. Okay, so in engineered systems, in machinery, you have the physical world that exists, and then you have industrial computers that run the machinery. Okay, and those two worlds have to be modeled in a computer. And they used to do it on paper, right? They used to do it on paper. We have the benefit of digital tools now. We can do our digital system modeling, and so we will model the machinery, and then you model the physical world, and then you see how those two interact, and that saves time and effort and money when you actually go and produce the machine, because you've sort of simulated how it works. And you don't have to make huge changes to the machine after it's designed. Right, so machine vision and machine learning kind of go together, two sort of fundamental manufacturing skill sets. And then control systems and system modeling I already talked about. I want to do a pilot program with this in January. That next January. I think it'll be a little rough in January, but I want to get something on the table so that we can get going something. But I really intend for this to be a very project-oriented workshop. I don't want to just be showing PowerPoints. I want people that are interested to actually be doing the code, and relating what they're doing there with whatever we're going to be doing in the work sessions with the CAD. So it's all one big happy family. You know, you need to do all this design work in the computer. You need to do all this programming, and then you actually have to have designs for the physical machinery, and then it all has to work together. So it's quite involved, but it's rewarding at the end of the day if you're interested into it. Pretty valuable skill sets. So that's sort of the rough plan as it exists. Let's see if there's any questions. Doesn't seem like it. So yeah, that's what I'm looking at here. And like I said, today I'm not gonna do a ton. I'm just I gotta get back into this. I've been away from it for a while, so I'm gonna struggle a little bit with this OnShape. I'm not that familiar with this CAD system, although I'm getting better. You can see that we've done quite a bit of work on it. There's not that much to go left. Last time, I believe, I finished up this ball screw bracket. Let's see, and attached it to this red saddle plate. Is this big enough? Let's see. Hopefully that's big enough now. So we got this ball screw bracket and attached to this red saddle plate. And of course, when the ball screw turns, you can see it's sort of a screw. The ball screw turns, the bracket will pull this red plate back and forth on top of these bearing rails. Okay, what we are missing is a flexible coupling, a gear reducer, and a servo motor. So the servo motor turns, the gear reducer reduces the speed from the motor shaft and increases the torque on the output. And then the flexible coupling protects, basically only transmits the rotational force from what will be the gearbox here to the ball screw shaft. And it will, we don't want to translate anything else to the ball screw except for torque. We don't want to introduce any lateral or longitudinal forces to the ball screw. Those don't do us any good. Okay, so I will continue on. Again, the Discord server is in the YouTube bio. Pop in there if you want to ask some questions. I'll also be watching the what programming is required for linear slide assembly. Can you... Not sure I quite understand the question, Christopher. Could you Could you maybe explain a little bit more about what your question is there? Okay, well, I'll continue watching and maybe put on some music like I did before. Oh, okay. You mentioned the physical. Yeah, so I think it'll become clearer as we get into this is really a piece of a larger assembly. When we do more complete machinery, I think it'll fall into place. What drives this ball screw, this servo motor, is motion controller, which I'm not familiar. There's a ton on the market, but it's a specialized industrial computer, and there are a variety of APIs and programming languages each of them support to basically read in sensor data or read in a program. So, for example, if we were to imagine this is part of a CNC machining center, and there's a part on top of this red plate here, and that part is being machined by something, there are specialized programs for the motion controller that take in G code. It's called G code. It's a specialized programming language for machinists. It reads the G code and then it knows exactly how to move the part against the cutting tool to machine the material away. Okay, that's it's not like a general purpose computer. It's a specialized computer that has, generally speaking, that has special software on it. Software that's baked into it that lets you make a variety of machines easily. I guess that's the easiest way I can describe it right now. It's actually a very good question. I mean, there's more basic industrial computers that we're going to need to get into that also have special programming languages like PLCs, programmable logic controllers, and that's a natural place that we'll have to start. It uses a programming language called ladder logic, which you can kind of see here. And there's a whole lot that we're going to have to do to learn that. And that is I would say that is probably one of the most fundamental industrial programming languages that exists. If you know ladder logic, which is a little foreign to start with, but if you know ladder logic, you can go really far on the shop floor. It's really one of the more fundamental programming languages. But from this, there are inputs from sensors around the factory or on the machinery, and then there's some logic performed based on those inputs, and then there's outputs that are triggered based on the logic in the middle. Okay, so you know what I'm talking about. Okay, so that's a fundamental one. And then above that, you have programmable automation controllers and you have motion controllers, which again support a variety of programming languages, Python, C++. And from there, you can write your own programs to do some custom, whatever needs to be done for the machinery at hand. And there's some pretty exotic machinery out there, of course, and we will be covering a little bit of it, but I don't know exactly how yet. We will need to broach it, but I don't know exactly how yet that I can do it. That's part of the challenge with the physical workshops, is that at the end of the day, to really learn this stuff, you kind of have to sit down with an actual controller and get familiar with it. But I think before then, there's quite a lot. There's quite a lot we can do. Anyway, good question. Hopefully I answered it. It was a little messy, but maybe in time it won't be anymore. Okay, so no problem. I will continue on with this for a little bit, probably another hour tonight. And if there's any more questions, pop them into the chat and I will answer them. Try to put on a little music. Hopefully we don't get banned, or I think it's copyright free music. What did I have last time? I have this. Copyright free beats. Let's see. Ooh, that's not. Alright. Sorry about that. So right now I'm going to be adding the flexible coupling to the end of this, and then we'll have to extend this base out so we can mount the gearbox and the motor. Right now it's a little short, everything's hanging off the end here. This is what they kind of look like, by the way. There's 2 bores on either end. This bore here will attach to the ball screw. This thing in the middle is sort of like, you can imagine it's sort of like a spring, like a 3-dimensional spring. It's springy in the middle. That is so when the input turns, it doesn't put any force, any lateral force or longitudinal force. So longitudinal with the axis of this ball screw and lateral being radiating out from it. If you don't understand everything I'm saying right now, don't worry. We will go back to this in a breakout session with pictures, which is going to be important, I think, to understand this. But the middle here is sort of flexible so that it doesn't put any force on the ball screw end itself. It just provides torsional force, torque to the ball screw, which is important to protect the ball screw. Okay, so right now I'm just selecting sort of they're called bellows couplings. I'm selecting one to mount to the end of this ball screw. And then again, I will explain this entire drivetrain assembly from end to end up to the motor in a subsequent breakout session, because there's a lot of detail that you need to understand to size everything in here appropriately and to select it appropriately. There's a lot of choices about ball screw size, bellows coupling size, motor sizes, gearbox sizes. You got to know how to size all that stuff appropriately, because if it's not sized appropriately, the assembly won't do what you want. It won't move the load that you want. It won't move at the speed that you want. It'll have jitter. It'll be unstable. You don't want any of that. You want it to do what you want, so you have to size everything appropriately. Another question, what exactly will this assembly be used for? I don't know yet. Linear slides are pretty flexible. Again, they're sort of a fundamental unit of industrial machinery and automation. I intend to take this assembly once it's completed-ish, and we will use it in a variety of other assemblies, like the automation cell that I talked about at the beginning. We may do a sort of a CNC machine using something similar. We will do a gantry robot that uses something similar. So it's very versatile, which is why I sort of started with this. It's simplistic, but it's a building block that if I explain this thing sufficiently enough, we can use this idea, we can use the content of this assembly in a variety of other automation and robotics machinery. So hopefully that answers your question, but that was the decision behind that. is the reason behind the ball screw for high torque applications. It's actually the reason behind. Well, the ball. I mean, yes, but it's also because high torque, high speed, and the ball screw gives us a lot of application flexibility to do that. We will work on other machinery, though. In particular, if you were here from the start, I presented a path of machinery we'll explore. In particular, on the large tank welder, the axes on that will be so long that a ball screw will no longer work, and we'll have to explore other types of motion systems, in particular helical gearing systems. And we will talk of the trade-offs associated with that, because there are trade-offs associated with using ball screws, with using belt drives. We'll get into that too, belt drives, and and gear drives. We will explore all those because you will see those depending on the application. You will see those in the field. Good questions. Right now, all I'm doing is I'm downloading a CAD model for a 3D CAD model for the bellows coupling, but I may remodel it myself because, and this is something to know, when you're doing real work machinery and you're picking out all these purchased components from people, what ends up sometimes happening is that the model that is available for you to download is, I wouldn't say it's poor quality. It's just not. It's sort of neutral, and you don't get a good. Sometimes it's not suitable to even. You kind of have to have experience to know what I'm talking about, but it's. It doesn't play well with your assembly. It doesn't assemble right into the CAD system. And the other problem is sometimes it won't accept a material. You can't assign a material to it, so you get an inaccurate weight for your entire assembly. And we want an accurate weight because we want to know how much this thing weighs at the end of the day so that we can use it other places. So I generally model up everything myself, but I use the downloaded 3D model from the vendor as a reference point. That isn't me, that's someone outside the... Oh, sorry about that. Friday night. Busy, busy, busy. I'm just sort of looking this thing over to see if I want to model it myself. I think I do. Because they have, it doesn't look quite right. What are you trying to do here? I'm using with a part that I downloaded from the vendor's website. Again, it's sort of a dumb, I call it a dumb model. It doesn't really have the fidelity. It doesn't have the detail associated with it. It's just this import object. It's sort of a dumb import object. And I'm going to model this thing up myself so that when I need it later, not only can I assign a material to it and get a good weight, but when I need it later, particularly with these, you can order this coupling from the vendor with different bore sizes depending on the shafts that you want to support. So this side is the motor part, and then this part is going to be the ball screw part. I want to drive those sizes, those bore sizes, with a table, with a configuration table in the CAD system. So I have to model it up myself. Otherwise, I can't adjust these bore sizes as needed. And I want to do that. So, like I said, I generally download the model from the vendor website, but then I model it myself. Right now, I'm just getting a bunch of dimensions for it so that I can model it in its own part, essentially. Hopefully that makes sense. Probably see what I'm going to do in a minute. Okay, Chris, thanks for the questions. Have a safe flight. everybody. I think that's all for tonight. Just kind of an easy night, except that this coupling takes a long time to model up. You can see it's got a lot of intricate features on it. But anyway, I will see everybody on Monday, and then we will start the schedule next week. Monday, Wednesday, Friday. I'll be here modeling and taking your questions. And then next Sunday, not this coming Sunday, but next Sunday, we will probably do a breakout session on linear bearing load sizing. How to size these bearings. These bearings slide. There's rollers inside of here, rollers or ball bearings inside of here, and they slide against this rail. Very low friction, precise linear motion. And there's a fair amount of detail involved in how to select the size of the rail and the size of these carriages, these carriage blocks that sit atop the rail here. So that'll be next Sunday, but we'll continue modeling this thing up. Hopefully we get done with it next week, and then we can continue on with some more intricate machinery. So let me see if there's any questions in the Discord. Doesn't look like it. A lot of good questions this time. Everybody have a good weekend, and I will see you on Monday. Thanks.